Video number 6 in our lovely series of sequence and series videos is about geometric sums. Now you'll notice I have a geometric sum with an r equal to 2 here. We're multiplying by 2 each time to get to the next term. Very simple sequence. We also have a sum formula here, and I'm going to show you where that comes from. Unlike the other formulas I showed you, there's not a real logical way to remember this one. This is one you're just going to have to memorize, but I will show you how it's derived just as a matter of interest. So this is actually going to be on the next page of your notes if you're looking at this. So this is deriving the geometric sum formula. Notice that I have just a general formula for a sum. S sub n is a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. So you're adding up n terms. Now if I multiplied the sum formula by r on both sides, I would get r times s sub n equals r times a sub 1, r times a sub 2, r times a sub 3, etc. Now what you might realize is in a geometric series, if I multiply by one term by r, I get the next term. So r times a sub 1 is actually a sub 2, and r times a sub 2 is actually a sub 3, and r sub a times a sub 3 is actually a sub 4, and so on. R times a sub n minus 1 is actually a sub n, and r times a sub n is actually a sub n plus 1. But I'm just going to leave it as r times a sub n for our purposes. Now, if we go through then and we subtract the second line of terms from the first, a sub 2's cancel out, the a sub 3's cancel out, the a sub 4 would cancel out with whatever's next in the top row. The a sub n minus 1 would cancel out down here, a sub n would cancel here, and all we would have left is the a sub 1 in the top row and the r times a sub n in the bottom row. So we could simplify this by saying s sub n minus r times s sub n is equal to a sub 1 minus r times a sub n. I'm going to rewrite a sub n because I recall from what I learned about geometric sequences that a sub n is equal to a sub 1 times r to the n minus 1. So if I simplify this, so if I multiply that by r times a sub n is r times a sub 1 times r to the n minus 1. Well, I can rearrange the terms since multiplication is commutative, and I can switch the order in multiplication. So I'm going to say a sub 1 times r, and this is r to the first, times r to the n minus 1. And recall that when you have two numbers that have the same base and they have exponents on them, you can add the exponents. So if I say, so this would be a sub 1 times r to the 1 plus n minus 1. Well, 1 plus n minus 1 is just n. So r times a sub n is equal to a sub 1 times r to the n. So I'm going to, having done all of this kind of off to the side now, kind of put it in a little bracket here, I'm going to take this, my result here, and substitute it in right here for r times a sub n. So now I'm going to have s sub n minus r times s sub n is a sub 1 minus a sub 1 times r to the n. And the reason I'm doing that is because I obviously want to create a formula that only involves known quantities. And I know the first term, I know what r is, and I know how many terms I want to add up. So that's a sub 1 and r and n. I know those, so that makes a great formula. Now I want to simplify this a little. On the left-hand side, I just want to have s sub n. So I'm going to factor s sub n out, and this would leave me with 1 minus r in parentheses. On the right-hand side, I could factor out an a sub 1, which leaves me with 1 minus r to the n in parentheses. And then I'm going to divide both sides by 1 minus r. And that's where the formula comes from. S sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. Now we're dealing with exponents. When we deal with exponents, we have to be especially careful when you raise something to a power, because if r was a negative number, we're going to have to be a little careful. We're going to see that in an example. But that's where the formula comes from. So back to the first example, which is a simple example. We have, this is actually part of a very famous problem called the checkerboard problem or the grain of rice problem. It's called different things. But the story goes that a man invented the game of chess and presented it to the king of a country, and the king was so enthralled with this new game that he promised to reward the inventor of the game whatever he chose. And this inventor said, well, I really don't want much. I just, on this chessboard, which has 64 squares, give me 1 grain of rice on the first square, 2 grains of rice on the second square, 4 grains of rice on the third square, 8 grains of rice on the fourth square, and continue to double the grains of rice to all 64 squares, and that's what I want for my payment. Well, the king thought, not a bad deal, just, hand a little bit of basket of rice for this wonderful game. So he agreed. So let's figure out how many grains of rice this man actually got. And you're probably guessing, he's bamboozled the king in some way. So we're going to use S sub 64. Our first term is 1, so A sub 1 is 1. And then R is 2, so we say 1 minus 2 to the 64th divided by 1 minus 2. Now, if you just do a little bit of analysis here, you'll notice in the top, or the numerator of the expression, 1 minus 2 to the 64th is going to be a very large negative number. But the denominator is also a negative number. 1 minus 2 is negative 1, so a negative divided by a negative is a positive. So we end up with 1 minus 2 to the 64th divided by negative 1, and that turns out to be a very large number. It turns out to be 1.846 times 10 to the 19th. And this is a decimal number that goes on grains. And being the nerd that I am, I actually looked up to see how much grain that really is in tons. What I did was I had a bag of rice, and I figured out how many tablespoons of rice were in my bag of rice, and then I counted every grain in that tablespoon, which was a lot, and multiplied it to find how many grains were in the bag, and then a bag weighed 2 pounds, and so forth. And I just kept playing with this number till I got my result. And it turns out that this is 373 billion tons of rice, which is a huge amount of rice. In fact, it is so huge, one of my students said, do they even make that much rice? So we looked up in 2007, one of my classes looked up 2007 world production, not just one country, world production of rice was 716 million tons. So basically this inventor asked for far more rice than even existed in the world, particularly back in that day. So he bankrupted the kingdom. Clever man, must have been a mathematician. Now let's apply, that was a pretty simple example. Let's apply this to a more complicated example. Here we have a sequence, and notice this is the one where, if you're not sure, remember you can always say r is equal to, and take the second divided by the first, negative 5 over 1, the third divided by the second, you can see they're the same, negative 5, the fourth divided by the third, and so forth. And it turns out to be that negative 5 is r. So r is negative 5. So notice we're adding. We have a negative number, then we add and we get positive, and then we subtract and we get negative, then we add and we get positive, we subtract and we get negative. So it's going to jump back and forth between positive and negative. And we want to find the 12th sum, or the sum of the first 12 terms. So S sub 12 is equal to A sub 1, which is negative 1, times 1 minus r to the 12th, negative 5 to the 12th, all over 1 minus a negative 5. Now I want to emphasize that these parentheses I'm writing around the negative 5 are not just decorative, they are very important. In the denominator, we have 1 minus a negative 5, which becomes 6. In the numerator, we have 1 minus negative 5 to the 12th. Now the question is that a negative number or a positive number? So if you say 1 minus a negative becomes plus, you'd think that was a positive number, but it is really not, because the negative 5 by order of operations has to be raised to the 12th power first. When you raise a negative number to a positive power, you get a positive, I'm sorry, not a positive power. When you raise a negative number to an even power, to the 12th power, you get a positive number. So we're saying 1 minus, this is the same thing as saying 1 minus 5 to the 12th. It's a positive number, which turns out to be, and then we have, I'm sorry, then 1 minus 5 to the 12th is a very large negative number. You multiply it by negative 1, it becomes a very large positive number. You divide it by 6, you get a positive number. The correct answer is 40 billion 690 million 100 and, no, I think I read that wrong. 40,690,104. Now, if you had carelessly put it into your calculator as 1 minus negative 5 to the 12th, and you'd thought, oh, make the negatives cancel out, or maybe you hadn't thought the negatives cancel out, but you just entered it in your calculator without parentheses, you would have ended up with incorrectly get my pen working there, incorrectly negative 40,690,104.3333. So notice the answers are very similar looking, and you might, when you're checking a problem something, think that you got the answer right, or think that maybe there was a typo on my answer key, but really they are two completely different computations, so you need to be very careful with your positives and negatives when raising something to a power. So keep that in mind. That is the end of geometric series.